Hey,
So our next speaker is Kiseok Yeon, who will be talking on the Hasse principle for homogeneous polynomials with random coefficients over thin sets.
Okay, thank you for introduction and thank you for giving an opportunity to present the result. Today I'm going to talk about the Hasse principle for homogeneous polymers with random coefficients over thin sets. As in the abstract described, first part of this talk will give an overall history for problems of confirming Hasse principle for projective varieties, and will give the classical approaches through the circle method to verify the Hasse principle, and we will give the main motivation of our results, and we will finish this talk by giving the statement of result at the end of the slides. Okay, here is the notation we are going to use this talk. E of z denotes e to the 2 pi I z, and we use bold x for s-dimensional integer vectors, and we use the bold x is between 0 and x when each coordinate is lying on this range, and a is less than b means a equals big O of b, and we also use a and b are asymptotically same when both a is greater than b and a is less than b hold. And we also use the bracket for the inner product. Okay, we begin with the definition of Hasse principle we are going to use in this talk. We are going to say an algebraic variety over Q satisfies the Hasse principle when this variety admits a point over R and a QP for R primes P, if and only if the variety admits a Q rational point. We notice here that one direction is trivial because Q can be embedded in R and QP. So the matter is to show the other direction. We are also going to say this variety satisfies the smoothness principle when the fact that this variety admits a smooth point over R and QP for primes P implies that the variety admits Q rational point. Okay. In 1962, Birch proved that a variety defined by R forms are homogeneous polynomials with integer coefficients of degree d satisfies the smoothness principle when the number of variables is large enough in terms of dr and dimension of certain singular locus. More precisely, this number of variables is enough to verify the Hasse principle for variety V. Okay. And around 60 years later, this vector, huge amount number of variables, can be improved to R times D times D 2 to the D plus R. You see that this vector is quadratic in R, but this one is linearly growing in R. So yeah. And in 2017, Browning and Heath-Brown proved a variety defined by system of forms with different degrees satisfied Hasse principle. Okay. Let's narrow our attention to the specific case, R equals 1, that is a variety defined by a single homogeneous polynomial. The Hasse-Minkowski theorem shows that the Hasse principle holds for a variety V defined by a quadratic form. For a cubic form, Heath-Brown proved non-singular cubic forms with n variables have a non-trivial integer solution. And later on, a series of Hollis work verified that has a principle for non-singular cubic forms in 9 variables. And for a quartic form, in 2019, Marmon and Vichet proved that smooth variety defined by quartic form satisfies the Hasse principle when the number of variables is at least 20. In general, Browning and Prandtl proved that smooth variety defined by a form satisfies the Hasse principle when the number of variables is this amount. This is an exponential function in D, so it's a huge amount of number of variables. Okay, I'm going to talk about the classical approaches through the circle method to verify the Hasse principle. If you are given a non-singular form f of x with integer coefficient in n variables of degree d, and then we observe the following relation, integration 0 to 1 e of n alpha d alpha equals 1 only when n equals 0. Otherwise, it becomes 0. So if you look at this integration, mean value of a certain exponential sum, and if you change the order of integration and summation, and if you look at the sum end here, then by the relation above, this becomes 1 only when f of x equals 0. Otherwise, it becomes 0. So this one exactly counts the number of integer solutions satisfying f of x equals 0. So to study this number of integer solutions satisfying f of x equals 0, then it suffices to study this integration. To do so, we are going to define major arc and minor arc. Major arc is basically a set of real numbers having a good approximation to rational numbers with small denominators. So that means the set of real numbers and having small denominator have good approximation with a rational number with small denominator. And otherwise, we this minor arc is just nothing but complement set of major arc inside the interval 0 and 1. So by using these sections, we are going to write this integration into two, mean value of our major arc, mean value of a minor arc. And if you have enough number of variables, you can deduce this mean value of a major arc becomes this expression, product of p-adic densities and times the real density and main magnitude. And this, and this real density can be interpreted by some surface measure of real hypersurface defined by f of x equals 0. And if you have enough number of variables, then this mean value of minor arc becomes error term. Okay. Okay, let's assume that f of x equals 0 is everywhere locally solvable. Then under that assumption, we can show that product of p-adic densities and real density are away from 0 by using Pensel's lemma and the implicit function theorem. So again, record this asymptotic formula. Since we just proved that, I see that, so that this constant is positive. So if you take x sufficiently large to get rid of the effect of error term, then it is it has the same magnitude with x to the n minus d. Okay, record that number of integer solutions satisfying f of x equals 0 is same with this mean value. And we just obtained this mean value has magnitude with x to the n minus d. So that means the number of integer solutions it has a magnitude x to the n minus d. It is not 0, so we just found integer solution of f of x equals 0 under the assumption that f of x equals 0 is everywhere locally solvable. So we just proved this variety we satisfy the Hasse principle under the assumption that if we have enough number of variables. Okay, that's the classical approaches method. Okay, conjecture about the Hasse principle. Whenever n is greater or equal to d plus 1, where d is greater or equal to 4, a smooth variety V defined by a homogeneous polynomial in n variables of degree d satisfy the Hasse principle. This conjecture will be true if Collier-Thielenn conjecture is true, but we'll not talk about this conjecture anymore in this talk. You see that our current knowledge are really far from this conjecture, because if you go back to the slide telling history, if you look at the third one, fourth one. Okay. Marmon and Vichy requires 28 variables, but if conjecture 1 is true, then 5 variables is enough. And in general, Browning-Prandtl requires this amount. This is the exponential function in D, but if the conjecture is true, then d plus 1 variables is enough. So it is still very far from the truth. So Funan and Volak in 2003 suggested a probabilistic point of view about this conjecture 1. To describe this, we are going to write a homogeneous polynomial in n variables of degree d with integer coefficients by inner product of integer coefficients and monomial vectors. For example, about binary cubic form. It's just inner product of 1, 2, 3, 4, and x, y, and x, y squared. This one. This order is just lexicographical ordering. So that means we notice that the dimension of this integer vector is exactly the same with the number of monomials, n variables of degree. Okay, and we are going to write f sub a of x for simplicity. And consider a variety VA defined by fa of x equals 0. This variety depends on the choice of the coefficient. Okay. And define a set of these varieties. Height of this coefficient is at most a. And Funan and Volak conjecture that proportion of varieties in this set, which satisfy the Hasse principle, converges to 1 as the height goes to infinity, provided that n is greater or equal to d plus 1 and d is greater or equal to 3. We are going to call this one conjecture 2. Okay, if conjecture 2 is true, then we can say that conjecture 1 is true in this particular probabilistic sense. And this conjecture 2 was proved by Browning, Lubadek, and Zawin, except for the case d equals 3 and n equals 4 by using geometric numbers. Okay, let's move on to the next slide. We want to emphasize this slide because this slide mainly provide motivation of our result. Our goal is to investigate the distribution of these integer coefficients with height at most a, whose associated varieties VA do not satisfy Hasse principle. To do so, if we take some set C, a subset of integer vectors, and consider a set of varieties, the height is at most a, and a is restricted to this set C. And ask a question, how many varieties do not satisfy the Hasse principle? If you take this C by a set having single element, then this question becomes conjecture 1 because we fix the coefficient and ask this variety satisfy Hasse principle or not. And if you take this C by just whole integer vectors, then this question becomes conjecture 2. So you can regard this question as just an intermediate question between conjecture 1 and conjecture 2. So with more answers to these questions for various sets C, then you will have better information about distribution of a set of coefficients whose associated varieties VA do not satisfy the Hasse principle. Okay. And in 2017, Brudon and Dietman took this set by a set such that each element inside this set, the polynomial becomes diagonal form. So that means they choose coefficients of diagonal forms and take an average. And they proved that proportion of varieties VA in this particular sets do not satisfy Hasse principle converts to 0 as A goes to infinity under the assumption that the number of variables is at least 3D plus 2. It's not, it does not match with the conjecture 1 though. It's still, this required number of variables still growing linearly in D. So it's powerful result in comparison with the previous result. So let's move on to, let me describe our set C. Define P of A by a non-singular form of degree k, and define integer vectors parameterized by this polynomial P. And consider a set of varieties. The height is at most A, and this set is restricted to this thin set. We are going to call thin set because this coefficient restricted to this coefficient parameterized by another polynomial, and investigate how many varieties do not satisfy that. Okay. To provide the statement of main result, we need the following two quantity. The first one is the proportion of varieties in our thin sets admits Q rational point, and this quantity is the proportion of in our thin sets which admit a point over R and QP for all primes P. Then we observe that the quantity of difference between these two quantities denotes the proportion of varieties VA, which do not satisfy the Hasse principle. Because if you look at denominator of this quantity, then denominator exactly counts the number of varieties, admits a point over R of n QP, but does not admit a Q rational point. So this quantity is the proportion of varieties do not satisfy Hasse principle. And here is our main result. P is a homogeneous, arbitrary non-singular homogeneous polynomial of degree. And then P of A equals 0 has a non-trivial integer solution. Then whenever D is greater or equal to 14 and K is less than equal to D, and N is greater or equal to 32D plus 17, then we have the proportion of varieties which do not satisfy Hasse principle converges to 0 as the height goes to infinity. We emphasize that number of variables still linear in D. So, and also we can take any arbitrary non-singular homogeneous polynomial here. Okay, thank you.
Are there any questions for our speaker?
I have two questions. One of them is a clarification. Can you remind me what capital R equals 1 is at the beginning?
History.
Yeah.
Capital R equals, yeah, that is a number. It's a number of, okay, here is, okay. So we are going to focus on the variety defined by a single homogeneous polynomial equation, not system of.
Oh, okay.
Homogeneous
R is the number of.
Yeah, R is number
Okay.
of systems.
Thank you. Sorry, the other thing
Yep.
is the densities you're using for your theorem, is the height you're using Euclidean height?
Yeah,
Okay.
it's a L infinite norm.
All right.
Okay.
Thanks.
Any more questions? Let's thank the speaker again.